But it is my incredible pleasure to introduce two great speakers tonight. The first of them is about to give you this talk is Dr. Chelsea Huang, who arrived at UniSQ during the time of COVID as a prestigious DECRA fellow, which probably for most of you means very, very little. The Australian Research Council, which funds a lot of the research here in Australia, has several different kinds of awards where you apply to the government for funding, and if you're successful, you get money, and this is good. The DECRA scheme is the Discovery Early Career Researcher Award. Typically in a given year, there are several hundred applicants, and only 10% of them get the funding. And both Chelsea and George are such world luminaries that they were both successful and are here, funded by the Australian Research Council, and will hopefully be here for decades to come, never mind years to come. So Chelsea is a real world expert. I believe she's going to tell you a little of her story during her talk, so I should shut up and let you enjoy her. So please welcome Dr. Chelsea Huang.
Hello, everyone. Can you hear me well? Yeah. Hi, I'm Chelsea Huang. Before my talk, I would like to acknowledge of the traditional honor of the land we're meeting on here, the Yarrawa and the Gadigal peoples of Toowoomba. And I would like to pay respect to their elders, past, present, and emerging. To start my talk, I want to tell you a story that 6 years ago about I got the lifetime of opportunity to work with a NASA mission that's aimed to hunt for planets around other stars. That is the Transiting Exoplanet Survey satellite. So today will most be a personal journey and insider story about this NASA mission and satellite. So at the beginning of my talk, I would like to share a quote that inspired me to it's not playing. Oh, to get into astronomy and physics. In my high school, this quote is actually from a really obscure short story, sci-fi story in Chinese. So I just tried my best to translate it for you. It says the beginning of a civilization is when someone starts to look at the night sky and wonder what is out there. It is, no worries. Yeah. It is by Chi Xinliu, who actually later on got Hugo Award for his three-body problem, which predicted one of the exoplanets found around Alpha Centauri, which is quite cool. I couldn't stop myself wonder about this question, what's out there, when I see the night sky, especially when they are as beautiful as this one. Oh, actually, I think it will start working now. No worries. Yeah, technical problem is always there. This photo was actually taken by one of my new PhD students a few nights ago at our local observatory, Mount Kent, and you can see the beautiful Milky Way on the night sky, and the sky is just littered with stars. So the question is that, are we alone? Is there any other planets out there? Of course, we're not alone in the solar system, in the term that there are other planets in the solar system. We all know there are actually 7 more major planets besides our Earth. They're quite different, one from each other. The biggest ones are Jupiter and Saturn. They're about 10 times the size of Earth and 300 times the mass of Earth. We call them gas giants because they are full of hydrogen and helium. The medium-sized ones, Uranus and Neptune, they're about 4 times the size of Earth and 16 times the mass of Earth. We call them ice giants. And then the inner rocky planet that looks more similar to our Earth, but only Earth has the capability of stardust civilization. But Sun is just a mere average star in the Milky Way. What about and we can actually, for the solar planets in the solar system, we can actually be really lucky to study the planets in the solar system. At the beginning, when we start to launch rockets, we send probes to Jupiter. And recently, we have be able to send helicopters to land on Mars. This is really cool video of Ingenuity taking off and landing on Mars, just taken last year. So what about all the hundreds of billion stars in the Milky Way? Are there planets out there? Since I'm giving you this talk today, you must know the answer to that question has to be yes. In fact, the first planets found around other stars was quite many years ago, about 30 years ago. And this is the first planet that we discovered around another star. It's called 51 Pegasi b. It is what we call a hot Jupiter. It looks like nothing we have in our solar system, although the size and the mass of the planet are really similar to our own Jupiter. But it orbits its whole star on a really crazy speed. In fact, 1 year on the 55 Pegasi b is about 4.23 Earth days. Just to remind you, 1 year on Earth is 365 Earth days. So it's a really short year on 51 Peg b if you live on there. Of course, you can't actually live on there because the planet is scorchingly hot. It's so close to its host star. The surface temperature there can probably melt in metal. So no one can live on this planet. But that's why we call it a hot Jupiter. It's like our own Jupiter, but really hot, environment-wise. And you might heard about this planet because the discovery of it won the Nobel Prize in 2019. This is for discovery of the first planet out there. Since the discovery of the first planet, we start to wonder, are there more out there? And all astronomer wants is just to find more of them. And in 2009, NASA launched this dedicated mission called Kepler to search for more planets out there. I was in undergrads back then, actually. And this is actually the first exoplanet mission NASA launched to search for planets. Kepler is a really big spacecraft. This is its sun shield. This is the spacecraft itself. The mirror itself is about 1.4 meters wide. This is its fairly big detector array here compared to a human. And it really revolutionized our view of what's out there. The Kepler mission used this method called the transit method to understand a planet out there around another star, because we could not actually directly see those planets with our eye or cameras. What is the transit method? This is a video showing you the 2012 transit of Venus. You're gonna see Venus cross the surface of the sun. This is just because Venus' orbit happened to align with our Earth's orbit and the sun, and Venus will be in between us, from Earth as the observer, and the sun. And as you can see, while Venus is crossed in front of the sun, it blocks out a tiny bits of the light of the sun. If you happen to have a camera staring at the sun, you'll find out the sun dimmed a little bit. I believe the next speaker, George, will actually have a really nice demo showing you this effect soon. So the transit of Venus is actually really rare. I actually believe I won't be able to see the next one in my lifetime. But luckily, because exoplanets and their host stars are so far away from us, so the chance of their orbits comes in between us and their host star is actually quite easy. This is what happens when an exoplanet's orbit happen to align between our line of sight and their host star. Similar things happen compared to Venus on transit. And this is just the amount of light we measure from Earth. And when the planet across the whole star, we just see this dip in the amount of light we measure around the star. Because the planet orbits the star periodically, in real life, we actually measure a periodic signal and keep on repeating in the data we measure around the star. So the transit method is really good at telling us about the size of a planet. This is quite simple to understand. Here we're comparing the transit of a big planet versus a small planet. As you can see, the big planet blocks out a bigger chunk of the light from its host star. Therefore, the star dims more during the transit events. and we see a stronger transit signal. This is how we know the size of the planets out there. So later on, if I tell you we found an Earth-sized planet, we found a Jupiter-sized planet, that is how we understand. So the Kepler spacecraft stared at a specific patch of sky for about 4 years. If you're in the northern hemisphere, it's really easy to find out the patch of sky that the Kepler spacecraft stared at. This is the Milky Way, and this is the brightest star in the summer night sky in the northern hemisphere, Vega. And if you happen to recognize the constellation Cygnus, Kepler field is right in between that. You can see this is a pretty small patch of sky. Just by staring at this small patch of sky, Kepler mission was able to find out many planets out there around different stars. This is just a bar plot showing you the number of planets discovered against year all the way till 2014, actually. What you want to look at is the green bars. 2009 is when Kepler launched. And after that, the number of planets discovered while the transit method just exploded. And we suddenly know there are lots of planets out there. Here is showing you a mosaic of the various planetary systems the Kepler mission discovered. I'm going to play a video later on, but here's just some instructions of what to look. Each of these circles are planetary systems. The little dots on the circles are the planets. The bigger the dots are, the bigger the planets are. And the stars are going to be in the center of these orbits. When I started to play the video, the planets are all going to start to orbit their whole star. And they're going to orbit at a speed that their regular orbit would be, except the time taken here would be in days and would be a lot faster than in days. As you can see, before I started playing this video, that the various planetary systems that Kepler discovered all looks quite different from each other. And now I'm going to just let the planet start orbiting. As you can see on the outer edge of the video, the planets are orbiting their stars quite slowly, but the center bits, those are the planets that we don't have in solar system at all. They are orbiting their whole star at a crazy speed. I told you about the hot Jupiter that's orbiting its whole star every 4 days. So they have 4 days a year, but some of the system in the center will have even crazy years. So this is really cool to look at all the strange system that we never ever would imagine exists that's out there. I'll just let it zoom in and let you see some of the really, really crazy orbiting planets there. So what Kepler has told us is that many stars out there have planets. That is the most important take-home message. Planets are definitely not a unique thing in the solar system. And if we just look at everywhere in the sky, there should be planets. We just haven't found them yet. If you just happen to have the ability to floating out of our Milky Way and look at our Milky Way from a place far, far away, and also every star we know that has a planet back then in 2018 will lit up like a really strong light. This is what the picture would look like. So this is our Milky Way, and our sun is here. And all this lit up part are the planetary system that we know back then in 2018. This really strong cylinder of light is the main Kepler field. So Kepler stared at this tiny patch of sky and found lots of planets in its line of sight. These little side streaks are because after Kepler's main 4-year mission, it lost one of its reaction wheel. So we have to repoint the spacecraft towards a few different patches of the sky and looking for planets after that. And that's why we have also have planets here. So one important thing to note is that the scale here of these streaks are about 5,000 light years. That's super, super far away from where we are. So we know planets that's really, really far away from us. What about planets around stars near us? I will just zoom this figure in to much closer to our home, the solar system. And this is what the stars around us with known planets looks like back in 2018. Again, solar system in the center, and the science circle has a radius of 100 light years. This is what we like to call the solar neighborhood. You can see not many of the stars are lit up within this science circle. Why 100 light years, you may ask? If I say that's because I can actually travel there within my lifetime if I jump on a light speed spacecraft. That's probably a joke. But the more serious answer actually lies in the next talk, when George will tell you all the things we're going to do to identify the atmosphere features of the planet and learn what's actually on those planets. All the methods he's going to tell you require lots of light from the whole star. And because stars in this tiny circle are super close to us, so they are the brightest stars in our night sky. And only around those stars can we actually find planets that we can learn a lot about. And if we ever want to find biosignature or little green men, they are our best hope. So we didn't know many planets in that circle in 2018. Why is that? Are there actually stars in that tiny science circle? Of course, this is what all the stars look like if we display them in a sphere in that 100 light year circle. Stars have different colors. The bluer ones are hotter. They're the hot A stars. The more of the stars are the red ones. They're the tiny M stars. There are about 4,000 stars in that sphere. And among them, there are 500 of them, that's the yellow ones, kind of looks like our sun. And we really didn't know that many planets among those stars. And that's where the problem was. And just to zoom in to that 100 light year circle and show you what the problem is like. And again, solar system in the center, this circle is 30 light years. And this is the 100 light year circle. All the blue dots are planets discovered by the Kepler mission, and the white dots are from various other missions from ground-based telescopes. And our goal really is to try to fill in these circles and find a lot more planets around those 4,000 stars. This is where TESS comes in. Unlike Kepler, the Transiting Exoplanet Survey satellite TESS aims to do a population census of nearby planets in our neighborhood, and really trying to understand them. This is an artist's concept of what TESS looks like. I've heard the concept of this mission in my grad school and immediately get drawn to it. What happened is that I heard about the mission and really want to work for the mission. And during my PhD talks at a big conference, I just told everyone I really wanted to work for the mission. And then it just happened that the PI of the mission was sat in my audience, and that's why I got hired by TESS. And TESS, unlike Kepler is a 1.4 meter big telescope, as I showed you. TESS is really tiny. It's probably not as tiny as this one. I can have lights on quickly so everyone can see it. Yeah, this is the 3D printed model we made for TESS. I wonder if the audience can guess how big is the real TESS compared to the model. It's actually not too much bigger compared to this model. So these are the solar panels. These are the cameras. TESS has 4 cameras on it. And I'm going to show you how big one TESS camera is actually compared to a real person. That is how big a TESS camera looks like compared to a real person. You can hold it with 2 of your hands. That's one of the most iconic pictures we saw when TESS is building its prototype. The camera is not that much bigger than what people use for amateur astronomy on the ground. And this is how big the camera lens is compared to your hand. You can just hold it in your hands. It's really small. And that's when I joined the TESS team, when they started building these prototype cameras and lenses. And these are how big the TESS detectors are. Again, very small compared to a hand. Each TESS camera has 4 tiny piece of CEDs, and this is what it looks like when you put them together. And 2017 is when I joined the team, and they started to build the real tests. And this is what the actual camera goes onto the spacecraft looks like compared to a human stand next to it. This is the sunshade. Again, as you can see, although this is slightly larger than the prototype, but it's still quite small. The bigness is actually mostly because of the sunshade. And this is what it looks like when the spacecraft actually get assembled. And the hardware team, again, also took this really nice photo of Tess with its solar panel extended. So I don't actually work for the Tess hardware team. What do I actually work on? I sit next to my computer and start to write the software that hopefully will reduce the data that Tess will download eventually. So that's what I spent my 2017 doing while all these cool things are happening in the lab. But 2018 come, and they finally wheeled Tess into the hangar at the SpaceX hangar in Florida. This is when the software team finally gets some activity and get really excited. We start to pack our bag to go to Florida to see the launch. This is the software team at MIT taking the photo at launch day -3 on April 13th, 2018. And in the back is actually a fake test model, which is quite really similar to the real test model size. And again, photo test launch -3 days and 5 hours before we leave. And on April 15th, we get to Florida. We got our launch pass and we take nice photos at the NASA vertical assembly building and looking forward to the launch the next day. And the next day, April 16th come. And we got turned around when we got onto the bus to the actual launch site. The launch got scrubbed on April 16th, which is really sad. And back then, we actually had only one launch window afterwards. That's 2 days after. And that's because NASA is planning to launch the Mars mission immediately after that. If we miss that launch window, we'll have to wait for many more months before we can launch tests. So next day is quite nervous wait, and we try to kill up our time by visiting museum to look at Saturn V, which is really cool. And we also take some photos of the alligator nearby. So the next day, April 18th, is the actual launch date, and I really couldn't sleep that morning. So the launch site is actually across the river to a parking lot of an obscure steak restaurant. So I got up super early that morning at 5 a.m. and drove to that parking lot and used shitty camera, take this photo of Tess, sit on top of a rocket, and rocket is vertical. That's a really good sign the launch is going to happen that day. And I claim I'm one of the first person to identify the rocket was vertical that day. So we wait for the entire day, afternoon, going to the launch site in the evening at 4 p.m. This is when we are actually at the launch site, much closer to the rocket. Still there, so that's great. And this is 3 minutes from launch, and you see what's going to come into you. Of course, I'm going to play the rocket launch video for you. Wait, the sound is not working for the rocket launch. The sound is not working for the rocket launch. Sorry you're not hearing the sound, but as you can see, the grounds are shaking based on the screen. And it was really, really cool just to stand there quite near to the launch site. You can actually feel the heat when the rockets start to launch the sky. And if you want to watch the full video and experience the sound, it's on YouTube. SpaceX makes really cool launch videos. So the launch is a success. And we take more photos to celebrate this, which is great. But that's when the hard work would start. after we left the launch site, we nervously wait for the spacecraft to get into orbits. And after SpaceX actually dumped TESS into orbits, they did a really nice thing for us. This is the photo of TESS that SpaceX took and sent back to us. And what's really cool in this photo is that here we have the first planet that TESS saw after its launch. It's our own planet Earth. Every time I look at this photo, I just feel it's so cool that we were able to look at our own little satellite looking at Earth in the background. TESS is actually on a really unique orbit. It takes a while for it to actually get onto the orbit. This movie will show you the weird orbit that TESS is on. So this is Earth, this is Moon. TESS is on a super elongated orbit that orbits the Earth every 13 days. And every 13 days, it will observe, staring at one patch of sky and just observe. And then at the orange bits, when it's super close to Earth, it will dump data back to us. And this is the first sense image that TESS actually passed back when we test the camera. And the team was super happy. It's like, yay, we saw stars. And this particular star that's super bright and have some really weird feature here because it's way too bright for our camera. It's Beta Centauri. I'm sure you can all recognize Beta Centauri in the night sky when you go out on a clear night. Yeah. And after that, we did some test data. We took 3 days of continuous data. This is actually the first exoplanet TESS saw. Actually, besides the team, no one knows this is the first exoplanet TESS saw because it's just our testing data. As you can see, this characteristic drop of light, and then the light return. This is when a planet across this whole star, and then left. This is actually a known planet that ground-based team found with their tiny telescopes in, I think, Chile. But this actually proves TESS works. We can find a planet that people already know about. And in the same 3-day segment data, we have saw more planets that people already know about. That's great. And then this is the real work happens. After the first months of observation, TESS sent back about several terabytes of beautiful images like this. So TESS has 4 cameras. Here is camera, I believe, 1, 2, 3, 4. And you can look at these images and find out how big a patch of sky that TESS actually observed. I don't know if anyone in the audience identifies some of the familiar features in the night sky. This is the large Magellan Cloud, and that's the small Magellan Cloud. And in this image, we look at about 500,000 stars at the same time. And we just started to really busy reduce this terabytes of data after that. Just to compare to what the Kepler field that is there for years, how big that is, it can fit in 1/4 of a TESS camera. That's why TESS can actually look at all the stars in the night sky eventually after a while. And after we reduce the first month of data, we have detected about 1,000 candidate planets in those data. And then we just sit together around the table, looking at those thousands planet detection and trying to determine which ones actually are really interesting planets. That's me lurking in the background, really happy about people looking at the candidates reduced from the software package I wrote. And here are some really interesting private communications between me and my colleagues. This is one of the first really interesting signal we detected in TESS. It's a really messy plot, so ignore that. But the point is that here we have this really nice dip here, which means a planet across the surface of a star. What's really interesting about this particular planet and this particular star is that this particular dip is actually really tiny. It tells us it's from a planet with size just slightly larger than us. And what's more interesting is the host star. It has test magnitude 5, which you probably don't mean anything to you, but translate to us observers' language, it's a naked eye star. Naked eye star means that if you go out to a really dark place, you can probably find it with your own eye. I can't because my eyesight are really bad. But this star actually has a name. It's called Pi Mensae. If any star has a name, that means ancient people were able to identify the star in a constellation and give it a name. So I sent this image to my colleagues at a different time zone at 10 o'clock. I think he didn't see the message for a while, but when he saw it, he got super excited and replied my message at 1:30 a.m. And like, yes, the signal you saw are real. This is so exciting with 2 exclamation marks. But that was quite cool. I will tell you a little bit more about this planet later on. But this is another funny thing about we almost lost the planet because we were so new at the job of finding planet with test data. So this is actually an Earth-sized planet with period about 11 hours. And 11 hours? I must get the period wrong. I'm so sorry. 0.83 days. That almost get lost in our data. So I basically told my colleague I found this interesting planet, and then I sent him a cutout of the image so he can reproduce my result. But he came back with this flat line, which you don't see the dip due to the planet. And we're like, where did the planet go? Did we misdetect something? What went wrong? But it ended up, I gave him the wrong star from the image. And after I correct that, and we end up finding this planet reappeared again, which is great. So in September 5th, we released these 2 planets to the public with beautiful NASA press images. I remember the dates vividly because the night before was my wedding anniversary, and I did not go back home until I think 12 a.m. of September 5th. And my husband was really not happy about that. But yeah, that's how much we worked actually right after test launch. It's basically day and night with all the data flooding and trying to discover planets. And this is the press release video that NASA made for Pi Mensae. It's going to zoom in to the star that you can actually see really well on the image. That's the star hosting the super Earth. It's orbiting its host star every 6 days. As I tell you, what's special about this planet is that the star has a name. But what's more interesting about this planet is that in its system, we actually has another planet that people has known for probably 15 years. And that's a Jupiter-like planet. So when we were sitting around that table, staring at these planets, one of my office mates just walked in and looked at the star name in a really obscure digits format that we astronomers like to use to identify stars. And she just recognized that telephone number Siri and say, hey, I know the star has another planet. And that other planet around the star is a Jupiter-like planet, but on a super, super elongated orbit. This is what the Pi Mensae system looks like compared to our solar system if we just have Earth and Jupiter. So that would be Earth's orbit, that would be Jupiter's orbit. And that's what the bigger planet in the system's orbit looks like. When it's closest to its host star, its orbit will actually cross with our Earth's orbit. But when it's furthest away with, from its host star, its orbit is going to cross our Jupiter's orbit. So it's a super crazy elongated orbit. And the new planet we found is orbit star on a super fast orbit. So the outer planet has an orbital period about 5 years, and the inner one has an orbital period of 6 days. We don't know why there's no more planets in between right now. And here's a sky guide of how to find Pi Mensae in the night sky if you have super good eyesight. I think someone has tried with a binocular and were able to find the star, but I was definitely not able to see it with my naked eye. And one of my PhD student, Alex Fenner, is actually trying to find more system-like Pymensae using another specific exoplanet detection method and combine it with the test data. This is a spacecraft that ESA launched. It's called the Gaia spacecraft. What Gaia does is to measure the position of the stars on the sky super precisely. And as you can imagine, when a planet is orbit the whole star, it's kind of like two person hand in hand skating together. It would drag the star moving on a much slower pace and leave its central position. So Gaia trying to measure this move from the star on the night sky. And this method is super good at identifying really long period planets like the outer planets in the Pymensae system, similar to our own Jupiter. And test data is really good at identifying planets with much shorter orbital period. So if you combine the two, you will be able to looking at planet system with a variety of different periods. So Alex is doing his PhD on looking for these types of systems. This is the other planets that we found. As I said, the orbit is 11 hours. So in our original message, we actually got the period wrong by 2 times, I believe. So that's how crazy the commissioning time was. So the other planet, as I said, is just a little bit larger than Earth. It's 1.3 times Earth's radius. And this is the nice movie of we zoom into the star and the planet starts to rotate. And although it has similar size to Earth, but it has much crazy system compared to our Earth because how close it is to its host star. The temperature on the surface of the planet is supposed to be 1,000 Fahrenheit, which should be fairly close to 1,000 Celsius, I believe. And with later on observations, people were able to determine the planet itself is permanently locked to its host star. So our moon is tightly locked to our Earth. That's why we say there is a dark side of the moon, and because the other side of the moon we never see from Earth. This is the same for this planet. There's a dark side of the planet, there's a bright side of the planet. Through ways that George will tell you a lot more about, we were able to learn that the day side temperature of the planet is going to be a lot higher than 700 degrees, but the night side of the planet will be super cold because it never get any sunlight. And we were also able to find out that it's likely there's absolutely no atmosphere on the day side of the planet. It's just bare rock, but super, super hot bare rock. And theorists also deduct that this planet might have a really weird tectonics because it's locked to its host star. So only one side of the hemisphere has really active volcanoes that create this half hemisphere of atmospheres. This planet is only 48 light years away from our sun, which is really cool. And I think I forgot to tell you the previous planet around Pymensae is only 60 light years from our sun. So you can see that only in the first month of data, we already have 2 planets adding to the number of planets we know in our solar neighborhood. Just an interesting side check. The planet LHS 3844, which is a long name, currently is in the naming competition of IAU this year. So there are a bunch of planets that IAU selected for the public to give the planet and the star names. And this year, LHS 3844 is among one of them. They're still in the process of welcome people submitting the names for the planet and the star. And if your name gets selected, these planet and star will be forever called that. So in case you're interested, please go check out their website. And if you're interested in any of the other planets, also give it a go. So one great thing about TESS is that it really enabled ground-based observers using telescopes from everywhere on the globe to looking at those planets. As I said before, these planet hosting stars are super bright. Some of them you can even see with a binocular. Therefore, if you have a reasonably sized telescope, sometimes even in your backyard, you can observe these planets. Actually, there's a really famous amateur astronomer, T.G. Tan, used his backyard telescope, observe some planets for us. It's really cool. Here, I'm just highlighting some of the observatories that we use over the globe to follow up the test candidates. And I would also like to acknowledge and pay our deepest respect to the indigenous elders, ancestors, and descendants who are the traditional custody of the land and waterway and skies upon which the telescopes used to follow up test candidates are suited. And we really like to thank them for sharing and caring for the lands on which we're able to learn. Without these telescopes, we will not be able to follow up all these test planets. Among all those telescopes, our local observatory and Mount Kent actually contribute quite a bit to following up some of the test planets. This is a really nice shot of the observatory from in the air. And these telescopes are the solar array, which are used for study the oscillation on the surface of the stars to tell us what type of stars they are. And these are the Minerva Australis arrays. It helps us measure the mass of the planets. We can also observe the transits of the planets through Minerva Australis now, and they really helped us with some of the test discoveries. And this is just me at Mount Kent, not using the Minerva telescope, but take a nice stroll. This is an anime of one of the planets that telescopes at Mount Kent helped discover with test data. This is TOI 3362b, another long set of numbers. But what's really special about this planet is that it's on an extremely weird orbit. It orbits its host star every 18 days, so 1 year is 18 Earth days, but that's not why it's so weird. As you can see that it's on a super elongated orbit, it's really similar to the outer planet that I showed you before in the Pymensis system, except that one has orbital period of 5 years. This one only has orbital period of 18 days. And the closest distance is to its host star. It's only 1/10 of the furthest distance is to its host star. So if you live on such a planet, your temperature changes by a factor of 3 in 9 days' time. It's super crazy. So the anime was showing you that the planet was orbiting the star, and when super close to the host star, it will actually become super hot and lit up. This is one of the really extreme planets that the telescope at Mount Kent helped discover. Another really cool thing that TESS can do for planets is to look at multi-planet system and time their orbits. So if you have a single planet orbiting a star, their orbital period should be like a really precise clock. So every time it transits, we remember the time, and it should just be exactly on time next time it comes along. And we just look at the planets in orbit after orbit, and it's always on time in this case. However, as I showed before, many of the planets out there actually has a few other planets in their systems. So what happens then? The two planets, if they're quite close to each other, will actually pull on each other's orbit and make this really precise clock, changing its time. So here on the other side, I'm just going to show you how the transit times from one of the planet just keeps on changing orbit to orbit. This is what we like to call the transit time variation. Just by measuring how these clock changes from the on-time version that we expect them to be, we can learn a lot more about these two planets, like how massive they are and how they are actually interact with each other. And one of our new PhD students, Emma Nabi, is actually using these methods and using Minerva Australis array to observe these planets found by TESS to precisely measure the transit times as a clock to understand how multi-planet systems interact with each other. This is just a really nice example of one of the planets that are found by TESS. Here we're plotting each transit observed by TESS. We're looking at how the observed time is different from the expected on-time transit time. You can see it just moves around, as I showed you previously, as the unprecise clock. So TESS launched in 2018 April. So what we do is okay, I'm going to turn on the light again. So what we do is we have one of the cameras pointing at the pole of the sky. Let's say it's the south pole of the sky. And then we will rotate the camera of the spacecraft every month. And in that way, in a full year, after full rotation, we would actually observe the entire night sky. And in the movie I'm going to play, we'll just show you a mosaic of how TESS actually map out the entire southern sky in a year of time. Yeah, so each of these strips are one of the 4 camera mosaic that I showed you before. And in the first year, it mapped out the southern sky. And in the second year, it mapped out most of the northern sky. We can't do this part of the sky because if we do that, the sun will get into our camera, and that's not great. But you can clearly see this beautiful image of the Milky Way in the test image once we put everything together. And this will show you a time lapse of the planets discovered by TESS after its launch. So we have 0, we call TESS object interest, meaning planetary candidates, as of August 30th, 2018. This plot is in period and radius, or size of the planet. So really short years, long years, Earth-sized planet, Neptune-sized planet, and Jupiter-sized planet. And you can just see we slowly discover more and more planets as time goes on. And as of today, I checked online, we had 5,900 planetary candidates discovered by the mission, which is quite great. And our other PhD student, Shishir, who took the beautiful Milky Way photo, is actually currently doing a project that uses artificial intelligence to search for thousands more new planets with TESS. Except this time, the AI will do all the work automatically instead of humans sitting around the table trying to discuss which one is a real planet. So the technique he's going to use is actually really similar to the technique you're going to have on your phone, trying to tell you whether a photo is a dog photo or a cat photo. So these days, if you have a smartphone, you go into your photo search bar, you tap in cat, or the cat photo shows up. You tap in dog, or the dog photo shows up. Except sometimes they identify pandas as cat. I don't know why. Probably because they don't have as many panda photos to learn from. But yeah, the way we do this is the same. We feed the computer lots of real signals from real planets, lots of signals from fake planets, and then tell it the truth, and it's trying to do the learn, and it's trying to identify planets from not planets. And the goal is that one day TESS terabytes of data come down, we put it through the computer, next day it spits out real planets. That's the dream. So let's go back to the figure I showed you before, that we have only 12 planets in the solar neighborhood. And after 4 years of tests, we have tripled the number of confirmed planets in this circle of solar neighborhood. But what I really want to show you is actually a interactive thing on NASA's website or of our Milky Way. So this is the one that I showed you back in 2018 when we have our Milky Way. Yeah, and can we zoom in? Like while going, zoom out, so the other direction, yeah. And keep on going. If we go into our sun, there's nothing almost. And then if we go to the other tab, this one. This is after TESS now with all our planetary candidates. And then if you keep on zooming, there's so many planet host stars in our neighborhood now. Some of this we're still in the follow-up process, trying to confirm with ground-based telescopes, but now we know a lot more planets, just within 100 light years of our sun. And hopefully one day, one of them will be nice to travel to. So that's basically almost the end of my talk. Just want to tell you that TESS is still ongoing. In the next 3 years, we'll finish mapping 100% of the sky. These are just obscure sky maps, and the white bits are where TESS hasn't been mapped. So you can see the first 2 years mapped about 80% of the sky. Until now, it mapped about 95% of the sky. But if you add the map of the next 3 years onto the other two, we'll have the entire sky. So we'll know basically every planet possible, all the nearby stars that will transiting. That's really cool. So to end my talk, just want to show you this really cool map of the Kepler field overlap with TESS CCD, and how Kepler, and this is the 4 TESS cameras, and how Kepler actually observed a bunch more tiny field. Those are the K2 mission after they lost one of the reaction wheels, and then how TESS maps the entire sky in a sphere. Yeah. And then I want to quickly acknowledge at the end of my talk, all the female scientists work at the TESS team. That's all of us. And I think the TESS team has been really encouraged the growth of female scientists, which is a really nice thing. And TESS is actually a mission with a female name. I think it's one of the first. Yeah. And what's the next step after we're finding all these brilliant planets? And that would be the next talk after the break by George. He will tell you all the cool things we can actually learn about all these planets that TESS is finding. Great, thank you.
So all those crazy orbits that you showed,
Yeah.
Are all of those explained by the theory of relativity, and can they be predicted?
A great question. So in exoplanet, we actually don't go into the regime of the theory of relativity as much. Most of the things we learn can explain by Newtonian physics, basically the equation of gravity itself. However, it's really hard to understand how those crazy orbits comes to where they are. So for example, in solar system, we think Jupiter are so far away from the Earth because at the beginning when planet formed, it's in a gaseous disk. And when you are further away from the star, the gas disk has a lot more mass. Therefore, Jupiter is formed much further away and it's 300 times the mass of Earth, but Earth is more inside and it's a lot tinier. So how does that big planet get onto an 18-day orbit and had such crazy orbits? So one of the theory that explains that is that the planet did something like birds do, migration. So somehow the planet get kicked into a super long, elongated orbit, similar to what we see on the outer planets of the Pi Mensa system. That's a 5-year orbit, super elongated. But the planet gets dragged when it's more closer to its host star, slowly dragged towards the host star. And maybe eventually it gets down to a super short orbital period. But that's just one of the theory that people are exploring, but we don't have the final answers on that yet. Oh, well, that's a really good question. So at the very beginning of TESS mission, it's obvious Pi Mensa because that's the first planet that we published. And it's really cool system around naked star. One of the more recent ones that has been recently published by one of my students, it's called TOI 2000 system. It's a large number. So TOI means test object interest, meaning planetary candidate. The number after that is how many of those we've discovered. So 2000 is the 2000s of the things we discover. So TOI 2000 is quite crazy because it has a Jupiter on a, I believe, 7-day-ish orbit. I don't remember the exact number. But then it has super Earth, a planet slightly larger than us, that's right next to the Jupiter's orbit. So we saw really few planetary systems like that. Just because you don't understand why those two planets can get so close and also get so near the host star. We always thought the giant planets like Jupiter and Saturn should be formed fairly far away from tiny planets. If they get too close, they will kick the tiny planet and eject them out of the system. So how do they get so close and both survive? It's a mystery. And that system, we also think we saw some of the, we call the dancing planet signal, the planets dragging on each other's orbits. And we might see some of the transit times has been inaccurate. So that could make one of my favorite systems. Yeah.
Thanks for this amazing talk. I'm just wondering, when you're looking out and looking for occultations, which cause the dip, presumably that's only a tiny fraction of the number of planets out there. So can you just give me an estimate of how many planets you could possibly see versus the number you never would see?
It's a great question. So yes, to see a trend, we actually need to be quite lucky. So the planets orbit its host star in random orbits. Only when they happen to be in between us and its host star, we will see this signal that we detect. So just to give you a rough idea, for the 500 sun-like stars we have in the solar neighborhood, if we were to discover a Earth-like planet on Earth-like orbit, we probably, assuming all of those stars have an Earth-like planet, we probably would see 2 out of the 500 that's out there. But having a transit planet has its really good advantages. George will explain all of that, mostly because we get to learn a lot more about the planet when it passes through in front of its host star. That's why we really like to discover transit planets. But yeah, it's a tiny, tiny probability that we see this planet. So the fact that we saw 5,000 now, that would say there are a lot of planets out there that we don't see.
So with the ones with the highly elliptical orbits, if you're only seeing the transit in front of the sun, how can you tell that it's elliptical?
Oh, that's a great question. There are actually a few ways to tell it's a highly elliptical orbit. We can do it with the transit alone. So this is quite interesting. So planets on a highly elliptical orbit, the planet would be with different speed when it's at different part of the orbit. When it's closer to its host star, it's going to be going around really quickly. When it's further away from its host star, it's going to go like super slowly. So the time it takes for the planets to go across the stellar surface would change depending on where you are at your elliptic orbit. So we can kind of estimate the time it will take for the planet to cross the star when it's on a circular orbit with certain period, and then use that to infer it has an elliptical orbit. But the more direct way to do it is actually use telescope like Minerva Australis array to actually measure the velocity of the planet at all points of its orbit. So this is called the radial velocity method. Again, George will give you a really wonderful demo about how we can measure velocity of stars and therefore velocity of planets. But the idea is really, it's like the Doppler effect. I don't know if you heard about that idea. So basically, when a thing is moving away from you and towards you, it will change the frequency you hear or see. And that's how we measure velocity. It will be super obvious when George takes out his demo. And if you can follow the planet's orbit every night and measure its velocity change, you will immediately know that it doesn't have a constant velocity, which is what you expect when it's on a circular orbit. And the velocity changes a lot. That says it's on a super elongated orbit. In this for this particular planet I showed, we were able to determine the elongation orbit with both methods, and they all agreed with each other, which is great. Yes.
Gwyneth has asked, she has met you and Duncan at a visit to Mount Kent,
Okay.
and she wants to know what is the most recent star or planet that Tess has discovered and that has been confirmed.
Oh, that's a really difficult question. Okay, so I will tell you this. This one is confirmed but has not been published yet, but it's really exciting. So there was this system called TOI 700. What's really exciting about the system is that, first of all, it has many planets in it, but more importantly, one of the planets in the so-called Goldilocks zone. A Goldilocks zone means the temperature of where the planets are not too hot, not too cold. Therefore, we think it should have liquid water and transfer life. So the big news is that they recently found another new planet in the system that's just slightly longer period than the original one. So one of the planets is on the slightly hotter end of the Goldilocks zone, another is on the slightly colder end of the Goldilocks zone. Both are in the magical zone that have liquid water. So they are just preparing for the manuscript of that planet. I think it's really interesting news to share. I don't know when the public will see it, but that's really cool. Thank you for giving me the opportunity to tell you about it.
So now we'll just take a couple of minutes. While George is setting up, George is the second half of our double bill, and it is a great privilege to have both these incredible scientists here working with us as UniSQ. You may have already guessed from some of the photos in Chelsea's talk that they are a genuine double act. And it was George who was a little bit upset about the wedding anniversary being interrupted. So they can have their arguments afterwards about that. They're a fabulous pair of researchers. George is also a DECRA fellow, which is, it's a real fantastic thing for any university to get a couple of those fellowships. It's a particularly incredible thing for a small regional university to get those fellowships, because a lot of them go to the bigger universities. So to have two people in the same field, given those fellowships to work together at the same small university is almost unheard of. And that's the caliber of speakers we've got here. It is really astonishing. And so I think George is almost set up. The reason it's taken a bit longer, as you'll see, is he's got some really kind of eye-catching and good fun little demonstrations to come here. So I'll give George the microphone and ask you to welcome Dr. George Zhao to the stage. Thank you.
Well, thank you so much for joining us. As with Chelsea, I want to acknowledge the traditional owners of the land who brought us so much knowledge about the cosmos. The traditional owners of Toowoomba, the Jarowa, and the Gadigal people. I also pay my deepest respects to their elders, past, present, and emerging. I want to talk about what Chelsea discovered, but I also want to talk about all the planets that we're finding that we can study, that we can tell what's on their surfaces. And perhaps one day we might be able to go and tell whether there's perhaps life on the surfaces as well. Over the last 20 or 30 years, we've been looking forward to this one thing launching. This is the James Webb Space Telescope. James Webb is a 6-meter space telescope. It's as large as some of the largest telescopes that we have on Earth. We launched it into space on Christmas Day last year, after a 10-year delay and after 10 more years of planning and building. It reached orbit safely on Ariane 5 orbit launch vehicle from French Guiana, and over the next couple of days, it unfolded itself. You see, the telescope is so big that we had to pack it tightly together like an origami inside the launch vehicle's fairing. But over a couple of days, it first unfolded this sunshade it has. The sunshade blocks the light from the sun so that we can turn on the sensitive instruments so that we can study the universe. You see, unlike other telescopes like the Hubble Space Telescope, James Webb operates outside of the range that you can see, outside of the visible light. Instead, it detects heat from objects. It detects the infrared. And so to do that, we have to block out the largest light source, the largest heat source in our solar system, which is the sun. And that's what this tennis court does. This sunshade does. It's the size of a tennis court. And it cools down the spacecraft to pretty much a couple of degrees above absolute zero. When this tennis court sized sunshade opened, it also allowed us to see the telescope and bid it farewell. And so from Mount Kent, we took this image, this movie of the telescope as it was traveling away from us 6 days after launch. That tiny dot that you see moving from the bottom left to the top right, that's James Webb as seen from Mount Kent here at Toowoomba. Pretty soon, it got so far away from us that we could no longer see it from some of our basic telescopes, but it kept on working its magic. The unfolding hasn't finished, right? We still have to unfold and unpack that tennis court size sunshade and unstack those sets of sunshades so that we can block out progressively more amount of light and heat and get the telescope as cool as possible. 1 month after launch, we unfolded those ears, that set of extra mirrors that we have, and made the telescope a telescope. We unfolded the secondary mirror support structure, and finally we're able to call this telescope operational. So much. 6 months later, we have this image from the spacecraft. This was about 6 months. It took 6 months, right? Chelsea talked about commissioning a spacecraft. It's not a trivial job. People work day and nights on these types of data sets, and it took about 6 months to get the telescope mirrors aligned, to get the instruments online. And finally, we have images from this great new observatory that we will have hopefully for decades to come. James Webb looks in the infrared. It's looking in the infrared because it wants to see some of the oldest galaxies that we have, some of the galaxies that were formed straight after the Big Bang. It's looking in the infrared because it can peer across the galaxy, look across the dust that blocks our visible light so that we can see some of the newest stars that have been born right now. And in particular for us studying exoplanets, it's looking at the infrared because we want to get spectra like this. It's not as exciting, I know, it's not as exciting as the images that are produced by James Webb and also by Hubble Space Telescope. But this is something that I've been dreaming about for the last 10 years. What we see here is a spectrum. A spectrum is like a barcode. It breaks up the light into its colors, into its rainbow. And within that rainbow, imprinted on it, is a barcode that tells us what a planet or what anything, any gas is made of. And in this particular case, it told us that this particular planet has some water in its atmosphere. That's not too surprising. Water is everywhere in the universe. It's composed of hydrogen and oxygen, some of the most abundant things in the universe. But it told us that we can detect the presence of water on the surface of another planet, and we can detect it at this exquisite precision that we've never been able to do anywhere from any other observatory. This is a gas giant. It's not capable of hosting life, but this is the type of technique that we will use over the next couple of decades, eventually with the goal of detecting what Chelsea called little green people. But how do we get there, and why are we doing this, right? I want to go back a step. I want to go back to what we know. We always fall back to what we know, and that's the solar system. We know the solar system well. We know that we have 4 terrestrial planets close in: Mercury, Venus, Earth, Mars. Then we have this divide. And then we have Jupiter and Saturn, the gas giants, Uranus and Neptune, the icy giants. We know the solar system so well because the solar system is tangible. We can physically touch it. We've traveled to the moon. We've had boots on the moon. We've brought samples back from the moon. We've landed spacecraft on Venus, on Mars, on some of the moons of the solar system like Titan, as well as on asteroids and comets. We've in fact brought material back from those bodies as well in many of these cases. We can study these material in labs and figure out what the solar system early on was made of. We've sent spacecraft to the outer reaches of the solar system. This is Voyager. The Voyager spacecraft is a pair of spacecraft that were sent out to the outer edges of the solar system in the 70s. Their mission was to explore Jupiter and Saturn. That was their primary mission. And then the spacecraft just kept on going. It's powered by this plutonium power source and just kept on going. Voyager 2 went on to explore Uranus and Neptune and provided us still to this day, the only images and data from Uranus and Neptune in situ. And now over the next couple of years, it kept on drifting away from the solar system. They're going too fast, we can't bring them back. And so they will forever travel onwards to other stars. But the power source that powers these spacecraft keep on diminishing. It's a plutonium power source. It keeps on diminishing and decaying. And so they have to keep the spacecraft alive. So they have to keep on reducing the number of science instruments that we power and reduce the amount of science that we return. It's also getting further and further away from us. And they were about to turn off the cameras to this spacecraft. But the great astronomer Carl Sagan convinced the team, and his team convinced NASA to take one more image by turning the spacecraft back towards Earth. And that's how we get this pale blue dot image that we know so well. It's often been said that everything you know, lies in that one single pixel, and that's Earth, taken from millions and millions of kilometers away. But that pale blue dot image is part of a much larger mosaic of the solar system, a family portrait. That family portrait for Voyager 2 contains Venus, Earth, Jupiter, Saturn, Uranus, Neptune. I think Mercury was lost in the glare of the sun. Imagine trying to figure out from that image that Venus and Earth are about the same size, about the same mass, but they are so very different that Venus is an oven. It's cooked with sulfuric acid and carbon dioxide. It's 400 degrees Celsius on its surface. And Earth is covered by 70% ocean and it has forests. Imagine trying to figure out from those images, from those dots, that Jupiter and Saturn are made of largely hydrogen, helium, but they're very, very different to Neptune and Uranus in their own ways. And that Mercury doesn't even exist in this image. And yet it's an important part of the solar system. Well, that's the job that we have. We have to figure out something about these distant worlds without even seeing them, right? Our job is even harder than this. We have to distinguish these planets from the starlight because the star way outshines the planets themselves. And we have to infer the presence of these planets, and then we have to infer what's on their surfaces and what their atmospheres are made of. That's the job that we have. I want to talk today about the tools that we're using to explore the surfaces of the atmospheres of the other planets. And I want to give a couple of demonstrations to tell you about how we're doing that, so that when you go and see on the news that astronomer detected carbon dioxide on another planet, you know what that claim is based on. And it's not just something that we made up and inferred, but rather through a bunch of different studies confirming, and a bunch of different telescopes confirming our studies and what we think might be on these planets. The first thing I want to talk about, well, I want to bring us again back to the familiar. I want to talk about Saturn. So this is what Saturn would look like if you were to take a telescope outside and if the sky ever clears. That's what you would see. You would see this beautiful planet, this gas giant, largely yellow in shape, largely yellow in color, with that oval shape because of the rings, Saturn, that unique set of rings. That's what you see with your own eyes, right? But what if we were to shift into the infrared? This is an image of Saturn that I took on the AAT, Australia's largest telescope, the 3.9 meter telescope at Siding Spring Observatory. And at this wavelength, in the infrared, Saturn completely disappeared. What you're left with is that ring structure that's made of mostly ice and dust. That reflects sunlight just fine in any wavelength. But Saturn has disappeared because Saturn's atmosphere has a lot of methane in it, and methane absorbs heat. For very much the same reason that methane is a greenhouse gas here on Earth. Carbon dioxide is greenhouse gas on Earth. And if you were to look at Earth at those wavelengths, Earth would also be dark. Saturn is dark in the infrared. And for pretty much the same reason, Titan, its largest moon, you can barely see it in that image as well, when it's one of the brightest sources of light next to Saturn. This is what we call spectroscopy. When you look at an object at different colors, that object looks different. And that's the essence of spectroscopy. By looking at an object at different colors, we can tell what it's made of. And in this case, we can detect CH4 or methane on the surface of Saturn, in the atmosphere of Saturn. But that's all great if you can actually see Saturn. Remember, our problem is that we can't even see these planets. We have to forward to another technique, and that's the transit technique that Chelsea talked about. This is an image of Pluto taken by New Horizons. New Horizons was a spacecraft sent to Pluto, our only exploration of this dwarf planet so far. And it took a bunch of great images showing this icy surface filled with tectonic activity because of ice that's as hard as rock moving on its surface. But then it traveled behind the planet so that the planet blocked the light coming from the star. And you should see nothing, right? The light from your only source of light has disappeared. But what you see instead is this ring around the planet, and that's coming from the tenuous atmosphere around Pluto. Pluto has an atmosphere. We knew this from the ground before we left, but we now know what it's made of because we can actually detect the gases from the atmosphere by looking at what the colors it's composed of. And we're making use of this technique for planets around other stars, except instead of sending spacecraft to them, we have to wait for them to transit. And so you have this tenuous ring of atmosphere around any planet that has an atmosphere, and you wait for it to transit. And some of the light coming from the star goes through the atmosphere and gets imprinted on the spectrum that we see with our telescopes. And so in this case, the planet might be fairly large in blue because it has an atmosphere that absorbs a lot of light in the blue. But if you were to look at them in another color, like in the red, it would look a lot smaller. And in some colors, the atmosphere might disappear altogether. And so by measuring the size of the planet in different colors, you can tell what the atmosphere might be made of. And so I want to do one quick demo here. So what I built this last night, right? So I have a really rudimentary setup here. I have a camera on one side, that's the red thing. I have a lens cap in the middle that's going to block out some light, pretend that to be my planet. Yep, thank you. Brilliant. I have this lens cap in the middle that's got some stuff around it. It's actually cellophane tape. The cellophane tape is going to be our pretend atmosphere around this planet. And I'll have my light source, a torch. And so what we hope we'll see is that the color will be different. Okay, so the blue line shows what our telescope sees in blue, and the red line shows what our telescope sees in red, right? And I'm going to slowly pass my blocking planet across the surface of that, across my telescope, and I see a transit. And the transit goes much deeper in the red than it does in the blue. Do it again. Deeper in the red than the blue. And that's because the planet absorbs all the red light, or my cellophane tape in this case absorbs all the red light, and that's the blue across. And that's what we do. We make use of this type of technique to figure out what might be on the surfaces or the atmospheres of other planets. This is actual data coming from James Webb Space Telescope for that one spectrum that I showed earlier. You can see here, and it's really difficult to see because the things that we're trying to detect is a lot more complicated, or is a lot more shallower than what I was demonstrating with that lens cap. But you can see that the light curve in green, that dip in green, is slightly shallower than the dip in red, by a little bit. And that's because the planet has a little bit of water in that red wavelength at 1.9 microns, and no water that's visible, and water does not absorb at 1.2 microns. And so the planet is slightly larger. And so when we show images like this or spectra like this, all we're saying is that the planet is slightly larger in one color than the other. And by looking at what the size of that planet is in different color, we get to figure out what that planet is made of, or at least what the atmosphere of that planet is made of. So I want to talk about a couple of projects that we're doing at UniSQ to explore other planets and to better characterize these planets that we're discovering thanks to Tess, thanks to the work of Chelsea and her team. The one project I want to focus on is the discovery of new young planets that we have around other stars. What do I mean by young? Again, we fall back to the solar system. We know the Earth very well. We know that it's made of that its surface is covered by 70% oceans. We know that we have this great, beautiful atmosphere that we breathe in every second that's made of largely oxygen, nitrogen. But the Earth wasn't always like that. Roll back the clock 4.5 billion years, and the Earth was nothing like that. The Earth was bare rock, a lava world perhaps, because the tectonic activity hasn't cooled down yet. And we had this primordial atmosphere, this atmosphere made of largely hydrogen and helium. That got boiled away by the intense sunlight from our young sun very, very quickly. This is called atmospheric evaporation. Now, we can't actually roll back the clock and look at what the early Earth was like, but we can discover planets around other stars that are newly born so that we can characterize their atmospheres and try to figure out what Earth might have been like or what Venus might have been like a long, long time ago. That's why we're at UniSQ, we're searching for planets around other stars that we think are young so that we can better characterize what the ancient solar system might have been like. And of course, we fall back to our good old friend TESS. You see, TESS orbits the Earth once every 13 days. And so I kind of just don't do any work for 13 days and then wait for that one data set to come down as the spacecraft rolls around Earth and perhaps bounces its data back down to the Deep Space Network here in Canberra. That's first orbit from TESS, 13 days worth of data, and then rolls back again, keeps on observing, and then 13 days later, it downlinks another set of data to us, astronomers. That data set quickly goes through Chelsea. As quickly as she could, she gives us the light curves. And what you see here is data coming from TESS that I worked on for 2 years. And it's nowhere near as pretty as what Chelsea showed with those beautiful dips showing you where the planets are. This is what a light curve that I have to deal with every day looks like. All that variation, that's coming from the star, not from the planet. So I'll give you 2 seconds. There are 3 dips there because of planets around that star. I'll give you a couple of seconds to try to see where they are. Here they are. So it's very difficult to tell where the dips are until we do some fancy flattening magic to this light curve. But we never really believed these dips ourselves, just as I'm sure in the audience, you don't believe these dips right now. And so we have to go to a different spacecraft to confirm them. In fact, here at UniSQ, we're one of the largest users of the European Space Agency's CHEOPS spacecraft. It's this 0.4 meter telescope in low Earth orbit. It's about the same size as TESS, but rather than 4 separate cameras on TESS, it has one large telescope about 0.4 meters in size. And unlike TESS, which is in a distant orbit around Earth, CHEOPS actually lies in a low Earth orbit 500 kilometers up in a polar orbit around the Earth. It's actually a sun-synchronous orbit so that the sun is always in the same position and the Earth is always in the same position. CHEOPS orbits the Earth once every 90 minutes. And so unlike TESS, where we can see stars all the time, sometimes the star that we care about gets blocked by our own Earth, and we have to deal with that. And so that's why the light curve coming from TESS, or the transit coming from TESS, looks slightly weird. CHEOPS looks slightly weird, but I'm going to break it down quickly. You have the first orbit coming from CHEOPS with those 3 dots on the furthest left, and the second orbit with those 3 dots following along. The light coming from the spacecraft, the light coming from the planet, from the star, is roughly constant. And then the third orbit, it dims by a tiny little bit, and then goes back up for the next couple of orbits. Just from that, we now know that this planet that we talked about just then around that noisy star is actually a real planet. One of our great graduate students, Natalie Losing, is making great use of CHEOPS. And in this particular case, this is data fresh from the telescope that's not published. downlinked about a couple of weeks ago, maybe 2 or 3 weeks ago, actually. And she detected these two planets transiting at almost the same time. These two planets are not that much larger than Earth, transiting at the same time around a young star that's newly formed with these new planets. Over the Christmas break, an undergraduate student here at UniSQ, Tyler Farrington, will make use of KOPS. He will actually point KOPS towards this planetary system with two planets. And instead of confirming the planets, he will actually try to measure the masses of these planets by measuring that transit timing variation, that clock motion of the planets that Chelsea was talking about. And finally, soon we'll welcome Sydney Vack, a new graduate student here at UniSQ coming to us from Harvard University as a Fulbright scholar. And she actually led the discovery of this 3-planet system by TESS around a young star for which one of these planets is in the habitable zone. It's in that Goldilocks zone where one of the planets has the right temperature for water to possibly exist as a liquid on its surface. We're not saying that this is habitable or inhabited. We're just saying that this particular planet is of the right temperature for us to explore what a planet in that temperature that Earth experiences might have been like 4.5 billion years ago. So we're discovering all these great new planets. And we're making use of some of the other great observatories that we have in Earth orbit to understand what they are made of and look for that escaping signature of hydrogen and helium. So we recently obtained time on the Hubble Space Telescope, a great observatory that was launched in 1990 that still remains in Earth orbit, still servicing the astronomical community, and still one of the greatest observatories that we have. You see, what we're trying to search for is that hydrogen and helium escape. And I thought about how to create that demo, right? How do you explain what atmospheric escape is like when we live on Earth and really our atmosphere is pretty static. It's not really changing that much. Well, the one way that I can think of would be the simplest demo I've ever done. That's atmospheric escape. We got helium in that balloon and I just let it go. And because it's lighter than air and because the Earth's gravity is so light that the Earth's mass is so light, we can't retain helium. And so it escapes. I'll probably get in trouble for that because that's littering. It will come back down in a couple of days. But imagine that balloon actually popped. That helium will escape our atmosphere. It's not going to be retained by the atmosphere that we have, and it's going to escape into space. And same with hydrogen, if I was allowed to use hydrogen in our balloons. That's atmospheric escape. Well, that was simple. That's the simplest prac that I've ever done. But detecting that around another planet light years away, tens of light years away, is difficult. Here's the idea. You have hydrogen and helium around this Neptune-sized planet. It escapes the planet. And so it forms this envelope of hydrogen and helium atoms around the planet. And soon, very soon, that planet loses all of its hydrogen and helium envelope, and it becomes this bare core. We're trying to detect that process because that process is visible in the ultraviolet. And that's what we're going to use the Hubble Space Telescope for next year in April. Ava Morrissey, a new graduate student here at UniSQ coming to us from Trinity College in Dublin, got time on the Hubble Space Telescope to observe the UV transit, the ultraviolet transit of a young star with a new planet that we hope will tell us something about how hydrogen is escaping from its atmosphere, and hopefully will tell us something about how the early Earth perhaps once upon a time had hydrogen escape as well. This is all great, using some of the greatest observatories in low Earth orbit and around Earth. But we can also explore planets around other stars by using telescopes that we have on Earth. We have a lot of them. All right, so Chelsea talked about the Doppler effect. The Doppler effect is usually explained to you as when a train goes towards you, it's got a high-pitched sound, and when it goes away from you, it's got a low-pitched sound. We've all heard that. I've got a quick demo for those people who,
Want me to
yeah,
follow?
do you mind? Thank you.
As long as I don't
Got a
get
quick demo.
Dopplered.
All right, so I stole a tennis ball from my dog. And on the tennis ball, I have a beeper and a battery. And I'm going to connect it up and it's going to make a loud sound. It's going to make a loud beeping sound. I'm pretty sure you don't want to stand there.
No, probably not.
As the ball is moving towards you, you should hear the pitch going a little bit more annoying. And as the ball is moving away from you, the pitch should be a little bit less annoying, but still pretty annoying, right? That's the Doppler effect, and that's what this planet is exhibiting as it's going around the star at a rate of about 200 kilometers per second. Now, remember, we still have the star. The star is also making an annoying sound. And this. I'm sure you can't tell one from the other because it's the same pitch. So I'm going to now play that sound and then whirl this tennis ball around me and see if you can pick out the difference between the two sounds. I saw some nodding of heads there. I hope that some of you were able to pick that out. So that's what we're going to have to do with the planets around. Thank you. Thank you, Jess. That's what we're going to have to do with these planets. We are going to have to use the velocity difference between the planet and the star to try to pick apart the signals between the two of them so that we can detect the atmosphere of one of these planets. So what we have is a planet that's drowned out by the light coming from the star. But instead of the star being stationary, we have a planet that's traveling around the star at a rate of about 200 kilometers per second. And so the star and the planet looks a little bit of a different color as it's going towards you and away from you. And that's because the Doppler effect, just like it has in sound, it also changes the color of light. Because light is a wave and it compresses the wave as it's going towards you and expands the wave as it's going away from you. And so it looks a little bit red as the planet is going away from you, and the planet looks a little bit bluer when it's going towards you. These are actually minuscule variations, but it's variations nevertheless. And so we have this planet that's changing in velocity as it's transiting from our point of view. And by measuring the changing velocity of that tiny signal during transit, we can distinguish between the light coming from the planet and that coming from the star, just because they have a slightly different velocity and therefore a slightly different color. Now, I have to be honest, we are only able to make these observations for some of the largest and hottest planets, the least likely to be habitable right now. And that work has been done by two of the graduate students that we have, that we already mentioned, Natalie and Ava. They're making use of some of the largest telescopes and smallest telescopes that we have on Earth to search for that atmospheric signal coming from the planet with this new technique that's actually only been developed in the last couple of years or so. But over the next 10 years or so, we will see a new generation of ground-based large telescopes come online. And the Giant Magellan Telescope, to which Australia is a partner of, will be built in Chile, and it would dwarf any of the telescopes that we have today. It's got this mirror about 24 meters in size, and it will collect more light from distant stars than any of the previous telescopes that we've ever had. And by using this telescope and by honing the techniques that we have right now using telescopes that we have, we hope that perhaps with the right type of star and the right type of planet, we might be able to detect things like molecular oxygen or molecular methane on these distant planets, gases that potentially might be because of possible life on other planets. Of course, nothing beats actually seeing the planet. And so in the distant future, we have this crazy idea. We're going to send a spacecraft into distant space. And we're going to send it so that it happens to occult another star. That is, it happens to unfold itself into a size of a couple of tens of meters in size and blocks out the light coming from another star just enough so that we can see the planets themselves. And so here's the, So here's the idea. You send a telescope with the star shade. As the telescope detaches, the star shade is going to unfold itself, and it's going to orientate itself in the correct orientation and the correct place and time, so that it happens to block the light coming from a distant star just enough so that you can see those distant planets. And by seeing those planets, finally, we might be able to take a spectrograph, place a slit on them, and actually measure what their atmospheres are made of once and for all. That's not coming for another decade or two, at least. We know from James Webb Space Telescope how long it takes to build one of these large missions. But we hope that in the next decades to come, maybe the next generation of astronomers can make use of spacecraft like this and new space telescopes to measure the atmospheric signatures of small Earth-like planets around other stars. But today, what we have is a great team of astronomers here at UniSQ, making use of some of the greatest observatories that we have here on Earth and out in space to better understand the planets that we know today because of TESS, because of the missions that came before it as well. So thanks very much, and I hope that was of interest and shows off some of the great sciences that we're doing here at UniSQ. Thanks again.
Thank you again. Just daydreaming a little bit, but way out there looking into deep space, do you ever see anything that really surprises you, or is the universe pretty much standard across the board?
That's a really cool question. I think in the field of exoplanets, there's absolutely everything we've discovered has surprised us. We never thought from the very first exoplanets, the very first exoplanets were not found earlier because we weren't looking at the right place. We always were thinking that we have this solar system-like structure where you have terrestrial planets closer in and Jupiter-sized planets much further out. And so the team that were observing and searching for these planets didn't even look for these for Jupiters that are much closer in, what we call hot Jupiters today. And so it took another team with a slightly differently tuned technique to identify the correct planet that became 51 Pec b that we now know is the very first planet around the sun-like star. And even before that, we found planets around pulsars. We never thought to look for them in the first place. Later on, we thought that we'd find lots and lots of Earths around other planets. Instead, what we found was that actually the solar system may not be that common. What we found was that the most common set of planets out there don't look anything like the configuration of the solar system. Instead, we have super Earths and Neptunes. These are planets that are larger than Earth and a little bit smaller than Neptune, but well within the orbit of Mercury. Those are some of the most common planets that we know today. We still don't know exactly why they got there, were they born there, and how come we don't have them in our own solar system. And what does that mean in terms of whether our solar system is special or not? So those are some of the surprises that we've learned over the course of the last couple of years. I'm sure with James Webb Space Telescope, everything will be a surprise. I think that the one slide I didn't show was a detection of CO2 or carbon dioxide on a planet, again, a Jupiter-sized planet. So you kind of expected to have a little bit of carbon dioxide and a little bit of these other gases, but nowhere near as strong as what we detected with James Webb. And that's from the very first spectrum coming from a new instrument on James Webb. So I'm sure that over the next couple of years, we'll have more and more surprises. In fact, it's very difficult for me to come up with an example that we expected to happen for exoplanets.
The work that you guys have done, what's it doing to accretion theory?
Accretion theory?
The formation of solar systems.
Okay, so core accretion. Yeah, so one of the first reasons that people came up with to build a telescope as large as James Webb Space Telescope to search for or to understand planets around the stars. The idea is that when planets are formed, they kind of have traces of what they were made of when they were formed. And so if you have a planet that's formed very far out, it's going to have a lot more ice because it's really cold out there. And if you have a planet that's formed very close to the side, it's going to have no ice. The Earth doesn't have a lot of water on it, has a lot less water than many of the other planets out there. It just happens that we have liquid water. That's what's special. But Pluto has a crust made of water ice, for example. There are planets out there with a lot more water than Earth, just not in liquid form. And so if you take these planets and you understand what their atmospheres are made of, you might be able to see, for example, how much water might be on their surfaces, or how much of other things might be on their surfaces. And from that, you can tell where they were formed. And from that, you can tell whether they happen to have formed with core accretion at that region of the planetary disk, or core accretion from a different part of the planetary disk, or maybe some other mechanism altogether.
What material will the sunshield be made out of?
That's a really cool question. And I think you're going to have to ask the engineers at JPL, because I don't know the answer. I know that it's some kind of mylar material, but I don't know exactly what it's made of, because you have to be very careful that it doesn't tear. And that's one of the things that people had with James Webb, is that that sunshield, that delicate sunshield, started tearing halfway through the design engineering phase, and they had to kind of delay by 5 years to fix that problem. So I'm sure there are engineering problems coming up in the next decade or so that we're going to have to fix with that star shield idea, but that's a brilliant question. Thank you.
That might be a nice occasion then for us to thank George and Chelsea again for the fabulous presentation. Well, thank you all for coming along tonight. With this, we'll bring the kind of positivity to a close. If you do have any questions that you want to ask and you're feeling a little bit shy about asking them in front of the entire audience, please do feel free to come down and say hi to the speakers while we slowly wind things up the front here. But yes, once again, thank you all for coming along, and hopefully I'll get to see plenty of you again for tomorrow night for the next part of this fabulous festival. Thank you.